Okay, thank you, Doug. Thank you, everyone. Hope I will keep you alive after the lunch break. So this is definitely slightly different topic, but I believe it's super important and really fundamental because, as the title says, like open source is no longer just for software, and we are going to talk about the need for the open hardware and actually auditable and transparent hardware. And it's nothing less ambitious than the fundamental level at the silicon. So we're talking about the chips. How we call it in our presentation is like really this project. We got the first open architecture secure element. It's a real product. I will talk about that. And we really see that this is the missing piece, or people have been asking for something like that for a long time to securing the critical infrastructure. Why? It's because you can't base security on the black boxes. And that's what the chips are today. So let me start with the story. I think it's important for the context. So, you know, sometimes you end up in the meeting where you leave the room and you think, okay, this is completely different than I thought before, or this is something we should spend more time on it. And I had such a meeting back in 2019, actually, before we founded Tropic Square. And it was at Satoshi Labs. It's a company who invented hardware wallet for Bitcoin. And these guys did an amazing job with open source software, thing which is very, very known to you. And software is perfectly positioned for transparency, auditability, quick fixes, all these features which really you need. If you find some issue, you need to react quickly. But what was the problem back then? It was the hardware. And honestly, still is, but we're trying to move the needle a bit or move the bar in the auditability at the hardware level. So really at that meeting, we end up with a question like, what if the sense of security is just an illusion? What we see today is in the chips which are black box, we don't know what they are doing, and they really require, vendors require NDAs to even start designing the electronics. And there was even one more dangerous question, I would say, because we were thinking, okay, but we can fix that. And before I will jump into how we're trying to fix that or move the things better, it's let's do the quick excursus to the chips and the history, because it's super, I think, relevant to why we see the security obscurity. So, predictions are very, very hard to make, especially if they are about the future. So let's leave the future for now. We might see, okay, maybe we win something what is really trustless. Like we want to not rely on the blind trust to the chips. We want to chips which are really secure. And to get there, it's a sort of journey which really started, back in 1947 with the invention of the transistor. And transistor is actually the product which was built since then in the biggest quantity ever. It's billion devices in your pockets, little switches, transistors, which made the semiconductor foundation. And back in the day, the devices were pretty simple. There were calculators and some other stuff, later printers, gaming consoles or cell phones. But back in the day, the data or the user security was not a concern. The only concern was the technology inside these chips, inside these devices. And the industry started to protect it by this obscurity concept. Basically, less people know about the details of the implementation, it was assumed to be more secure. But it's been proven by the time that it's not working like this. And the industry started, when the products were attached to some monetary value or some other incentives beyond just the use case, it started to change the landscape. And it started with reverse engineering industry. Reverse engineering at the silicon level was introduced by essentially or enabled by the printer cartridges. That was the point where people started looking at the chips and say, okay, maybe what if I look, inside, and what if I look at each layer and maybe try to replicate a chip? And today, it's a big topic, and these chips can be reworked without understanding what they're doing. You basically can just replicate them. The hacking of the gaming console, I think, was around 1995. Again, was a new kind of incentive for the attackers and for the, let's say, becoming the device security topic. The cell phones bring with the interesting use case of cloning SIM cards, obviously. These days, we live in data-centric era. Everything is connected, and what's changed, it's not much the security of the silicon, which we rely on in our devices, but really the value in the chain. Like the devices itself are commodities these days. They are not that important. They only enabling us to consume data or generate data. But by our usage, we kind of digitalizing our transactions, and this becoming the value. And really, this has to be protected. So it's no longer enough to stay with the obscurity, which works perfectly for the vendors, but kind of leaving the users dangerously exposed to the cybersecurity risks. Still, vendors say, we have a secure solution, it's covered, but is that really true? Why do we see headlines like these? Why it's easier for attackers than for defenders? And, these are because we're not living in the security era. It's an illusion of security where we are right now. And what can we do with that? So if there is really, the security, we know that exposed. Like the chips inside devices are black boxes, and we don't know what they are doing. Why is that? Why nobody asking for transparency in the chips if it's okay to ask for transparency in the food or finance industries? Why the chips are different? Why hardware is so different in this case? Let me give you an example. Imagine you are buying a house, and I'll tell you, hey, this is a nice house, super secure. There is a perfect fence, super high security locks on the doors, and so on. But here is the catch. You have no way to check it. You can either buy or leave it. And that's how we buy the chips these days. But what if I give you a similar situation and tell you, hey, do you want to buy the house? Well, let's stay a few days in, check how it's done. Here is all the documentation, how the house was built. And you can basically everything test yourself because there is no fence. And the fence, in this case, is not really security, it's just the obscurity. It's supposed to be a barrier for the attackers, but in reality, it's not. For the future, we will see what comes, but definitely, if we really need to, if we are heading to the era of the autonomous system, decentralized, agentic systems which will do transact on our behalf, the systems which are no longer centralized, where you can't revert the transaction. Everything has to be secure by design. And enable that, we can't rely on blind trust to some systems. Basically, the systems have to trust or have to gain the trust from the users. And that's a completely different thing. So if we can go this direction, we definitely should see less of these. And these are not really the admin credential type of problems. These are the fundamental problems at the silicon level. So what could be a solution? I mean, I already heard on the other talks today, like, it's a transparency auditability. But at the same time, it's just the enablement. If something is open source, it doesn't mean it's secure. But otherwise, it doesn't work. So you have to open stuff, and that's what we believe. Like, we have to move from the trust me bro type of approach to, hey, here is the proof, here is the source, it's designed to be secured, it's provably secure and auditable. So we go this direction with our solution, which is called Tropic 01, first product of the Tropic. Tropic, by the way, means or stands for truly open IC. So that's what we really, it's our mission, what we are working on, and we really want to make sure that the devices can be trusted, but not because you have to trust the vendor, but they can convince you and show you where is the barrier, what's the level, how the threat model looks like. So quickly recap what we are doing. So trying to solve the problem with the industry, with the cybercrime, exploiting undocumented features, vulnerabilities hidden inside the devices, which are not really in the focus. Semiconductor industry, as it is established, is not innovating fast enough and not able to react to this kind of shift of the usage of the devices when the obscurity doesn't work anymore and exposing the users. And for the security and cryptographers, it's not a new topic. It goes back to Mr. Kerkhoff, who said, a system has to be secure even if it's in enemy hands, which means all you need to protect is the cryptographic key. So our solution is our chip. It's just the first step on this long journey. But really what we designed is a secure element, which is type of device which try to do the minimum feature set, because more features means bigger attack surface and more problems. So we're really trying to keep the stuff minimum, keep it allocated in dedicated perimeter, which is external chip, and it helps us to protect it on the physical level. We are making sure that implementation of the algorithms is side channel resilient, it's fault injection resilient, which means that when you compute the cryptographic algorithms, the data, sensitive data, are not leaked by EM or power traces. These sounds like quite advanced topics or quite advanced attacks, but in reality, they are pretty basic, especially on the silicon, which is not taking care of these countermeasures. And the physical resilience, like even data extraction from the silicon is high on the stack to prevent that, because obviously we trying to protect the user's data, and there are the features I will talk later about that, how to do that, but definitely it's important to make sure that even if one chip is broken, it's not like easy to break the others. And thanks to the openness, transparency, and auditability, there is no place to hide the backdoors or kill switches, which is very important these days. In terms of practical stuff, we're really building on auditable silicon, utilizing the open source software. Open source chip design is a movement, or is a topic which is getting the traction past few days. And yeah, RISC-V is just one a buzzword or the name you might be familiar with. Basically, this is how slowly the chip design is moving to this direction. And definitely, chip design is very, very old-fashioned industry. So if you are already bored with the open source software, just on the software side, look at the open source hardware, because we really need help from the software engineering standpoint. A lot of automation and testing is really waiting to be aided on top of the traditional chip design. And if you don't know that, the chip design is really a different programming, essentially. We still design the chips like you write the code. So this is just to mention what Doug already mentioned. Like, we announced the chip early this year, been here at Nuremberg at the Embedded World Show in March, got an award. That's all great, but I don't want to bother you with this marketing stuff. I just really want to mention that because it's something we are proud of, and it's a huge achievement of our team. But the important part is that the chip is real. It's there. We have a dev kits. We're trying to enablement developers. And later today, there is a workshop where you can really enjoy using the USB stick with the Tropic-01. In terms of block diagram, as I said, like, we're trying to keep a minimal setup of features in the chip to make it easy to protect. But still, there is quite a few blocks. I mean, I don't want to go to the details, but really high-level stuff. There is some OTP memory. There are some fuses which you can configure, let's say the chip disable interfaces and so on, and you can prove that it has been disabled, because it can be proven by microscopy inspection, let's say. There is a flash memory, which is something you can't really protect that much. So then the encryption is the solution, how to make sure that, as the flash memory is a third-party IP core, which is not fully auditable, and we don't know the details. We just making sure that in our threat model, we not rely, or the chip security is not really relying on these features, because we assume that the data can be extracted from the memory. But there is this interesting part of the chip which is called PUF, physically unclonable function, and this is a piece of IP or periphery which generates the unique key based on the silicon production variabilities. So you can think about it like a random number generator, but the random number generator which always generates the same number. It's deterministic for one instance of the silicon. So if we use the PUF and derive the keys for the on-chip encryption, you store the data into two instances of the silicon, and you have a guarantees that there is basically different encryption. The data will look differently. So we're trying to improve or implement various advanced techniques. I already mentioned physical security, like anti-tampering sensors, laser, EM, and all this stuff. But also want to highlight these 5 key elements of the auditability, which means no undocumented features in the design, firmware source code available. We talk chips, but chips are not always the hardware. Actually, the opposite is true. There's a lot of microcode and a lot of firmware running on the silicon. And it's very important to understand which blocks use the firmware, where the firmware can be stored, and at the runtime, to making sure that basically there is no code which shouldn't be there. Threat model already touched on that. We can't do fully open chip these days. Or if we would do, it would not be this industry-grade level. So it would be the older technology just for kind of academic purposes. So in the threat model, we just making clear which devices are fully auditable, which source code will be on the GitHub, and which parts are really third-party license IP we can't talk about, but how we kind of address their limitation with our design. Test results, not just verification of the I don't know, API or anything like that, but really the results from the attackers who tried in the lab run these side channel analysis or EM analysis, laser fault injections, and all this stuff. And the hardware source is obviously important to really audit and enable what we started with. Market segments. Now, I want to illustrate one thing in this slide. We have a chip for 4 months now, and we are very early with this go-to-market and business activities. But what is really important that we already have various use cases in particular segments, and these segments they might have a different vocabulary, different language for pretty much the same thing, and it's the key applications which Tropic One can enable, which is the silicon root of trust, secure boot, HSM or PCB level HSM, if you wish, digital identity attestation, and obviously, as there is a flash, some encrypted storage on the silicon, but it's not like a flash disk to storing your movies. It's really for the fundamental assets which you need to use at the hardware, embedded electronics, some cryptographic accelerations. But in the end, all these features goes to this topic. It's about securing the identity of the chip, identity of the device, and enabling the authentication and attestation. And these are the fundamental features. Starting with the chip, we're working on making this easy. In terms of hardware electronics, it's very simple, straightforward, 4-wire SPI connection. We got a SDK on the GitHub, so API interfaces which you can straight integrate into your host application and start the development, and also supporting the popular embedded developers platform like Raspberry Pi, Arduino, or micro extension boards, and also the USB dongle. Okay, everything you can find on the website and the GitHub. That's not the important part, but now that's the important part. So today, we will be running the workshop in the other room here at 5 p.m., if I'm not mistaken. And we have prepared a bunch of the USB sticks for you. So really, this device, it looks like a USB key, you might know, like a hardware wallet or something like that. But really, the goal here is to enable and demonstrate the features of the Tropic 01. And for that, we have a utility called libtropicutils at the GitHub, which really brings you the command line interface to talking to the chip, and you can generate random numbers, you can generate cryptographic keys, get your public keys back, and so on. But for us, it's really vehicle, and that's the call to action for you. We would really like to trigger the discussion. So I would like to welcome you to the workshop. We have other dev kits for you as well. But really, the main message is let's just brainstorm and talk. How do you can see usage of that? Because we see a lot of stories about TPM is broken, or the encryption of the flash memories and so on. Some of them are really problem, like they're using just the symmetric encryption, and then the hard drive which is encrypted is delivered with the key inside, and that's the problem. So with the solutions like this, you can basically disconnect the key storage from the data which are protected, and we would like to really discuss and hear your opinion. So I guess that's conclude my talk. So thank you very much, and hope to see you at 5 p.m. at the workshop. And I don't know if we have time for questions. Yeah, go ahead.
Thank you so much. It has good. It has been a good presentation. My question is: do you engage yourself in research, and how have you looked at quantum key distribution? And that's a part of security. And the other side is fabrication of semiconducting chips like QPUs. Do you also go that direction?
Sorry, the first question was about the quantum key distribution?
Yeah, quantum key distribution with cryptography and key passing using photonics.
No, but we have customers who are in this space and trying to evaluate how we can fit to these applications. The Tropic 01 has a conventional elliptic curve-based cryptography, so there's no post-quantum on this product.
Okay. Yeah, the other question was to do with, since you said semiconducting chips fabrication, still I think since you don't do BB84 to do with cryptography, I think still you're not considering QPUs, quantum processing units.
No.
Okay, thank you.
Could you give a rough estimation about the entropy of these chips? And second question as a follow-up. These are now ready assembled PCBs. Can I buy these chips at these normal distributors like Mauser or DigiKey?
Yes, you can buy them. And currently on the Mauser and DigiKey is only the development kit. So the chips, like samples for your product, are distributed directly by Tropic. But the chips is in volume production and exists in the high quantities, so it's possible. And there was the other question, right? Entropy, yeah. Okay, let's take it for the workshop. I don't have numbers in mind. Like there's a true random number generator. The tests are looking great. And there's also the way how to do this quantum randomness guaranteed entropy running on the silicon. We have some proof of concept on that, so yeah, should be good enough.
Could you explain in a bit of detail why exactly you can't be adopting the TCG TPM interfaces for this chip and you need your own libtropic for that?
Why we can't use...
Why can't you just use TCG, TPM, 2.0 drivers rather than needing a user space library? Yeah.
The problem is like why we doing our own chip and not using the existing TPM is this black box aspect, the limited auditability. You don't know what's in there, how it's done, how it was tested, and so on.
No, I don't mean why you're doing your own chip. I mean, why are you doing your own software interface?
Yes. There was a big discussion about that, and there's kind of legacy in this UPDU and smart card interfaces, and we just wanted to do it kind of without this legacy, and we can do with the, like a module with the microcontroller, similar what's in there, like we can do the interface to behave for the external mode like a TPM or trusted computation group compatible interface. It can be done on the microcontroller, which manage the low-level API between our chip and the host controller. So that was kind of pragmatic design decision to have more flexibility, and now we are looking for these use cases, and we can easily mock up such applications and check whether it's traction or not. There's a question over there.
Yeah, my question is, how are you, in the future, how are you going to deal with the PQC part, which is provided by NIST for this? That is post-quantum computations?
Yeah, this chip is not addressing post-quantum by the cryptography implemented inside the silicon, and you can consider this a cryptographic accelerator. So actually we have there's a firmware which can be run on that, but I don't think the performance would be anyhow important. Like for the cryptography, post-quantum, you have long keys and it's different stories. So we're looking at this in our next product to address the post-quantum readiness.
And how is it different from HSMs, hardware security modules?
Yeah, that's a good question. So basically, you can see this chip as a HSM in the sense of being able to store the data securely, generate the keys, and so on. But it's similar to the previous questions, like the interface, is actually interface is done by the RISC-V CPU by the firmware. So maybe there is a way to implement minimal HSM-like interface inside the silicon, but it's not really the ambition. The ambition is rather to build it with the external MCU and do it as a module for this security. And you really have to bear in mind, like this is the first product, and we have to start somewhere. So it's not really, there's no huge team and huge resources to allow us to go this direction. But we believe that right now that we prove that the chip is really a reality, it exists, people can get aboard, can play with that. That's exactly what is super valuable, having these kind of discussions and trying to build these examples.
Okay, I have a question. So about practical use, is it possible with this circuit already to store like 500K bit wallet depth file, things like that? Or I need additional storage hooked up to this circuit?
I think 500 keys is probably too much, but you can play with the key derivation eventually on the silicon, so you maybe not need to store that much keys. It depends on the use case.
But from the circuit I see, it is possible to hook up additional USB device, like to encrypt it with a key inside the chip. Is it possible?
It is possible, and that's actually the target implementation. Like this is really the storage of the keys, and if you want to do the flash disk, which is encrypted, like with the other memory, then you have to have other, periphery to the host controller which manage this encryption, and the Tropic chip is just used as a vault for getting the keys for the decryption.
Okay, thank you.
Yeah. Okay, sounds like no more questions. So thank you very much and see you at the workshop.